Display register.
Display data.
Data register.
Yeah, this is the display status register, and this is the display data register. I'm going to use as a prompt, just because it's simple to work with, just a simple question mark. And let's see, you have to find the dumb thing here first. There it is. The ASCII hex code is 3F. Okay, that's the ASCII code for a question mark. Okay. Now, I'm going to write a routine that will do nothing more than just print this value out, this question mark. So here we go. Okay, we'll start at a different place. Remember, the first thing you have to do is be sure that the display is not busy. So you set up this little wait loop here. Where we're going to check that display status register. Okay, we do that by saying load indirect sum register display status register. Okay, once again, remember what that load indirect does is it says go to this location, then use the contents of that location as an address. So what we're actually doing is going out to this address, which again isn't a true memory location. It is sort of, because it holds something that looks like it's in memory, but it's associated with this device. We're going out to this location indirectly by going through this memory location, which is part of our program. Okay? Now, why do we have to load it? Because I have to set the condition codes based on the value that's stored in that register. That's what I'm getting after here. I want to look at those condition codes. Remember, the display status register looks like this. There may be other stuff in there, but this is the only one that we're really concerned about. Bit 15. Bit 15, if you look on page 205 here, he's got a map of the thing. And it works in this manner. When you put any kind of a value into the data register, then the system will set this bit 15 to indicate that the device is busy. Okay, so what we have in here is a 1 indicates that the device is busy. 0 would indicate that it's ready. Oh, wait a minute, I've got that backwards. When the transfers an ASCII code to the data register, the electronics of the monitor automatically clear bit 15 as the processing of the contents begins. When the monitor finishes processing, it sets the thing. So I've got those turned around. One says that it's ready, and the 0 says it's busy. Okay, so as I pull the contents of this thing into register 3, remember the load instruction is one of the ones that sets the condition codes. So I will branch if it's 0 or plus to wait. I'm just going to keep looking at that thing until I see a 1, which would make that number negative because it's the most significant bit. As soon as it comes out, I can now print my prompt. Well, I can just keep using register 3. And then I store indirect register 3 to the data register. Okay, I want to store this value out at this location, and I get there going indirectly through this memory location. And that will print the prompt. Okay, if that's all I'm going to do, it would look like this.
So the store indirect is storing R3 into the address of DDR.
Into the address that is stored in DDR.
So you use the store as an address and it goes to that location.
This is where it's going to end up, at FE06. That's where it's actually going to go. It does not go into this memory location because of the indirect. The indirect says, look here, use what's in there as an address and store it out there. Okay, whenever you have that indirect, it's a 2-stage operation. You go to the memory location specified in the instruction, and then you go from there, another hop, to the place you want it. Remember, one of the big reasons for this, remember in the instructions, you can only go so far. I can't store this address FE06 in an instruction. I don't have enough room. I have 2 alternatives. One of them is that I could store it like this, and then I could replace this one instruction here by the following. Load R4, let's say, from DDR, and then use the STR, the store relative to this register with this offset from this address in here, and this is the value that I'm storing. Okay? This accomplishes exactly the same thing, but it doesn't use register 4. And a little less computation, one less memory cycle, various other things. But if you want to think of it in this manner, this is what the store indirect is doing. It goes out here, fetches this address, and then uses that address as the place to store things. This is the whole idea behind a pointer variable. this memory location is pointing to the display data register. That's what's going on. Yeah.
On the branch, you have Z and P. I'm not quite getting that. If it's looping as long as it's 0 and positive, right?
Right.
Why would it turn negative when you when you do an entry?
The most significant bit is 1, so it's negative.
No,
This is always gonna.
it turns 0. When this is done, it will change this bit to a 0. As I come into this, that should already be 0.
Yeah.
Okay? If this is a standalone program, there should be nothing going out to that display. It should not go through that loop. But you do it for a reason that'll show up here in a minute.
I don't know, I may get shot down, but it's going to always be 0 and positive. If it's busy, it's gonna be 0. If it's positive, it's gonna be the 1, so that case is always gonna be true.
Yeah, but look at the bit that's gonna be a 1.
So is that just looking at the bit?
Well, no, it's looking at the whole thing. But what is it that determines whether or not a number in a memory location is negative? It's the most significant bit, and that's the one that's getting set. Okay, it's not changing that whole memory location to contain a 1. No, it's changing that one bit.
To be a 0.
Which is
0 or
positive
1.
and negative.
So it keeps on going 0, negative, 0, negative, when it's ready and busy. If it's ready, it's a negative, it's showing that significance.
Yeah, if it's ready, it has a 1 in that location, and then I will not branch, and so I can go down here and print that character out.
Yeah, that's kind of weird, but yeah. I get it.
Well, yeah, in a sense it's weird, but you know, it makes sense as you stop and think about it. It's a pretty efficient way of checking. If you had that ready bit as being bit 0,
You'd have to subtract it.
you'd have a lot more to do to try and find out whether the device is ready for you. But by making it the sign bit, hey, it's easy. Okay? Now, let's look at something a little bit different here. As you have seen, as we have gone through some routines to print values out and so on, they get kind of lengthy. And in this assignment, you've got 2 of those to do, 2 inputs and 2 outputs. They both get lots of code. Well, one of the things that you learn in beginning programming, at least we hope you learn it, is that anytime you've got big blocks of code that get repeated almost verbatim, you think, hey, separate those off, write a separate procedure to do that. Okay, so that's what we need to do here, is to look at how we can write a separate procedure to do what we want it to do.
Now with the homework,
Mm-hmm.
are we expected to be able to input any integer or just a single digit integer?
Any integer.
Okay, and so we'll have to loop and do the add by 10 with
Mhm.
everything then?
Here's the way the thing works, basically. We've got our main program here. And now I want to branch to a procedure. The instruction is JSR, and I'll just put a name in here, input. And then we go on down through, and maybe we call it again down here. eventually you'll get to the end of your main program. You may have some data kinds of things in here. Here's your code for the routine input. It will end with an RET.
So in this case, there would not be an end after the data?
No, because you've still got code after that. Remember that that dot end is a signal to the assembler that there is nothing more that pertains to this program. That's the last line of code. It doesn't mean end of data, it means the end of everything related to this program. So that the assembler will then stop processing lines and translating them. Okay, here's what the JSR does that you need to be aware of. It first of all has a little temporary location in here, and it copies the program counter into that temporary location. Now the JSR itself, let's see, we've got 4 bits for the opcode, which is 0010, 100. That's 100. Then it has a single bit here. There are 2 different ways of handling this thing, and the way you handle it depends on what's in that particular location. The one we're doing has a 1. Okay. Then it has in here an 11-bit offset. Okay, so it takes that offset, does a sign extension on it to get up to 16 bits, adds the program counter to it, and stores that in the program counter. And then that temporary value gets stuck in register 7. Now,
Always?
always, okay, you have no choice on that, which is one of the reasons why some of you got a comment on your papers, didn't lose any points, but now is the time to get in the habit of not using register 7 for anything else. Because when you get down to this thing, it does only one thing. It copies register 7 into the program counter, and that's all it does. Okay? RET assumes that the return address is in register 7. Now, that poses some interesting situations too. What if you have a subroutine that calls another subroutine? Well, if you do, then you better save register 7 someplace and restore it before you get to the end of the first subroutine so that you return correctly into your main program. You have to watch that. It's pretty fussy. Pretty fussy. Is this common? Well, not so much anymore. It was commonly used when memory was at a premium, and it still kind of sticks around. More common way to handle it now is to work with a stack, but this is the way this system works. Basically what you're doing is putting your return address into register 7. And then you're developing a new address, the beginning of your subprogram that gets copied into the PC. Because the computer ultimately is pretty dumb. All it does is it looks at the program counter and says, oh, that's the next instruction for me to execute. And it goes and gets it no matter what's in there. So the way to get to a subroutine is to change the value that's in there, like a jump. Okay, the only difference between this and an unconditional branch is that you are saving that return address so that you can get back where you were. Plus the fact that because of the setup of the thing, you've got a few more bits of offset and you can actually go a little farther than you do with an unconditional branch.
Will the compiler tell you if it's out of range?
I believe so, yeah. You can go quite a ways with 11 bits, if you think about it for a minute. Because it is a signed number, you can branch back or forward, either one. So you've got basically the farthest forward you can go is this, which happens to be 2 to the 10th minus 1, or 1,023. You can go over 1,000 memory locations. Now, there is a way to go beyond that. You get back into the pointer business to do it. This is a JSR. There's a JSRR, which looks about the same, except that it has a 0 in here. And then we actually have 2 more zeros. And then you have a register number, 3 bits for a register number, and then the rest of them are all zeros. What it does is this one does the following. Again, it copies the PC into the temporary location, and then it copies the contents of that register into the program counter, and then the temp into register 7. So if you can get an address that's farther away than this, full 32-bit address into that register, then you can branch anywhere. You can go anywhere as a subroutine. But it requires a little more in the way of instruction so that you can get the address of that routine loaded into some register. Now, there are some things to look out for in doing this. One of the principal ones is that it does not change any of the registers except register 7. If in my main program I have some important information in register 0 and my subroutine uses register 0, guess what? I just lost that information. Okay, so if you have, we'll talk from the point of view of the main program, but You talk about caller and callee or whatever you want, but if in your main program you have things in the registers that you don't want the subroutine to mess up, then you better stash them off someplace. Now, does that responsibility go with the calling program, with the main program, or does it go with the subprogram? You can say, well, if the subprogram is going to use any of the registers, then it needs to save what's in there and restore them before it comes back. Do it either way. You might do it, for example, this way. Let's stick a data value down in there. See, in my input routine, the first statement I might have is store register 0 at save 0. Now I can go ahead in here and use register 0, and just before the return I would put load register 0 from save 0. So then when I come back into my main program, register 0 is just like it was when I left. Memory is different. I mean, these memory locations, they have labels on them, and that's okay, but registers you kind of have to look out for. You have to be careful. So we do this kind of a trick. Okay, any questions about that? That's pretty high level, abstract thing. Well, let's see. We'll write this is kind of a dumb subroutine, but it's not one that you would normally do. Let's see. Well, that's all I really want to do. Now, where do you put A, B, and C and so on relative to your subprogram? It ultimately doesn't matter. You can put those things anywhere you want. Just a couple of rules. One of them is that you have to be able to reach them. If you've got a really big program, you're going to want to position those things someplace so that you can get them without going through too many song and dance kind of routines to get down to the end. The other thing is you want to be sure that you don't execute them as program instructions. That's why you have a halt before you do your data. This isn't going to be very long, so I'm going to do my adder routine here first. Add R0, R0, R2, return. Okay, and then I've got my A here with some value B, C, Now, notice that there's no way that I can hit this stuff to be executed. Because if I'm here, I'm going to hit this return, which is gonna send me back into here. If I'm up in here, I hit the halt, and I'm gonna stop executing. The halt has to come before your subprogram, by the way. What happens if I do this?
Add them all up again.
Yeah, it's gonna execute that subprogram again. Again, the computer's pretty dumb. It just goes on to the next location. It executes the instruction and just keeps going. So if you put the halt down there, it'll go down here to the subroutine, it'll do it, it'll return, it'll come back up here, it will fall down in and it hits return. Now what's it gonna do? It's gonna go to whatever's in register 7, and since I haven't modified it, it's probably still what was there when I did this, so it's gonna go back there, and I'm going to end up in an infinite loop. Because register 7 is never gonna get modified. Okay, so you have to be very careful about how things like that operate, and why you essentially have that halt before you have your subprogram. Halt doesn't mean that nothing after this point is going to be executed. What it means is when you hit this instruction, stop. That's what it means. Okay, that's
So when it executes that, it does the JSR, goes down to the adder, hits the return, and then it's done.
then it halts.
Okay.
Yep.
When it returns to the next line.
It returns to the instruction following the JSR. Yeah, because after all, that's what's in the program counter. When it loads this thing and starts deciding what it's going to do, remember the program counter gets incremented, and so it's pointing at this location. That's what gets stored in register 7, the address of that location.
Is there another program counter that takes care of the routine? The
Nope.
subroutine?
That's why you have to save it.
Okay.
That's why it gets stuck up there in register 7, because there is only one program counter, and it puts the address of adder into that one, and then executes. And then when it returns, the program counter gets set back to where it was. Okay. Any other questions? We're about out of time, and I'm about out of voice, so
Are we gonna go over the test next class session?
oh yeah, that's probably what we really should have done today, huh? Yeah, okay. Any questions you might have about the exam, we'll talk about them first thing on Wednesday. And I'm going to try and find out why my computer cannot talk to this projector.